really that much of a hassle for the students, but it is for us. Because what they do, they take them off the roll then, and then they put them back on the roll, and then I have to go back and put all their attendance in over again because we have to take attendance online. So please, if you know of anyone who hasn't paid, please say, look, pay by today. Get it started anyway. Okay. We are recording, and Lauren's here. Okay. I'll repeat it for your sake. Well, maybe I won't repeat it. No, I didn't know it was going to upset you that badly. There's one more battery under. Okay. The vice president sent an email. I forgot to print it out. I'm supposed to read the text from the email. And please pass this to any of your friends, classmates, anything else. I know there's at least one student who hasn't paid, but she hasn't been here at all. But if payment isn't complete by 5 o'clock today, those students are going to be removed from the roll completely. So just please pass that along to anyone you know who may not have paid yet. Okay? And like I was saying, they usually let them back in, but what you have to do is go to the vice president's office and I don't know what all, but it's a lot easier to go on and pay. So let them know that. Okay. Let me go and get this started from current slide. And any questions? I have received the first test in. Oh, I'm in the wrong section. I do hope I put 3. No, they didn't ask for it. We're in 3.3. I thought that was the page I was on. Yeah, and here we are on the quotient rule. Any questions on anything we've covered up till now? And here's Davis. So I'll say it again. The vice president sent an email that I was supposed to read in class today. I forgot to print it off. I read the email while I was not at a computer with a printer, and so I couldn't print it. And then this morning when I came in, I was busy trying to get ready for my classes today. My physics classes needed some things run off, so I was trying to get that done. And then I got stopped in the hall. It's been a crazy day. So anyway, here's the essence of the email. If a student has not paid by today at 5 o'clock this afternoon, they're going to be removed from the roll. Okay? And if that student has plans or has things in the work to get payment, for instance, one student in one of my classes needed a letter from the college to his college to get the financial aid transferred and stuff, and it took a while. I hope it's done by now because he's had the letter for a while, but I just, there are some things out there that could allow it, so, but they are going to remove people from the roll who haven't paid if they don't know anything about it. So if you know of anyone who hasn't paid yet in any class, please tell them 5 o'clock today their payment. If they haven't received it by then, or at least know that it's in the works, they're going to remove you from the roll. Okay. All right. Any questions on anything we've done up till now? Like I was saying before, I have received the first test in, which is good to see. Let's see, how many papers have I gotten in from this class? Let's see, let me add them up. 0. Okay, none. Okay, and our May is over with, and June is starting to be over with. So please, folks, like I was saying earlier, midterm starts today, this week at Thursday, right? Is the end of first. That's midterm. So please, folks, don't put it off, those papers off till the end, and never, or usually not as good a quality if you don't have time to review them, that kind of stuff. All right, no questions? All right, last time we did the product rule. Someone quickly tell me what the product rule is. If you have two functions, f and g, that are both differentiable functions, what is it that is the product of those functions? Number one, the product is differentiable, and what is the product rule? This is quotient rule, so you can't use it. So what would be the product rule? It's taking the derivative of a product of two functions. Oh, it was a long time ago. Had to have been at least 4 or 5 days. Product rule. The first times.
Yes.
Oh, yeah.
The derivative of the first times the second, and the derivative of the second times the first.
What do you mean and? Plus, exactly. That's exactly what you mean by that. Okay? So how about quotient rule? Again, the givens are here. F and g both have to be differentiable functions. Then f divided by g is also differentiable. For all x's, remember the other was all x's such that where they are differentiable. But now we also have the requirement that g of x, since g is going to be in the denominator, we have to exclude all the values for x that make g equal 0. Because, of course, you can't divide by 0. So we have to exclude those x's. Even though g is defined there, it just happens to be 0 there, and you can't divide by it. But in those cases, the quotient rule is not nearly as nice as the product rule. So here's what the quotient rule is. First, it's getting Will here. And once we got him here, all right, we'll continue. And I'm going to say this for everyone who comes in. I was supposed to read this, but I forgot to print it out, so let me just tell you. The Vice President sent an email saying that any student who had not paid by today, 5 o'clock p.m., is going to be removed from the roll. So if you haven't paid, or if you know of someone who hasn't paid, I think most of you have paid, if not all of you have paid. But if you know of anyone in that circumstance, they need to get by one of the offices and let them know what your plans for payment are. They may still remove you from the roll, but if they know the plans, I think they'll let you back in later. I don't know how they do that. That's not my function, except they make it our function that we have to sign the registered roll list and turn it into the Vice President's office by Wednesday. I don't know. Okay. Crazy how we do it. So here's what the rule is for quotients. If you're dividing f by g and taking a derivative of that quotient, now the first part starts a lot like the product rule. Okay? First is, but now this time, remember the product rule, I think one said derivative of the first times the second plus the derivative of the second by the first, or something like that, right? Okay. And I remember I said, well, you know, it doesn't matter what order you multiply or add, because addition and multiplication are both commutative. However, with the quotient rule, it does matter. And why does it matter? Here's a subtraction sign here. Subtraction is not commutative. So you start with the denominator, g, times the derivative of the numerator, minus f, the numerator, times the derivative of the denominator, and here's the other difference, divided by g squared. Okay? So it's a little more complicated formula. Number one is a minus sign, which makes the order mattering, and then you also have to divide by the denominator squared, which makes the whole thing a lot messier. Okay? Now, I think I've told you before about tutoring our Indian friend, son, and we're friends with him too. I went to his wedding, and no, we didn't get to go to his wedding, but we met his wife and stuff. But anyway, here's how he said the quotient rule, the way Indians talk real fast and do it. And I never thought I would do it. Okay? Now, in this rendition, F is called high and G is called low. Numerator, denominator, okay? They say low D high minus high D low over low low. low d high, derivative of the top, minus high d low, derivative of the denominator, over low low, the product of low times low. And the way he said it was low d high minus high d low over low low. Yeah, I went, what? But actually it's a pretty good way to remember. Just remember you start low, low d high, minus high d low, over low low. Start low and go to high. Okay? There's the quotient rule. Now, the proof of the quotient rule is a real, they do it in a very short time, in a very short space, but it requires some manipulation here. So, there is a little reminder here, and here's what they say in their caution. It is easy to mistakenly reverse the order of the two terms in the numerator because of that subtraction sign. Think of the, and here it is. They do it here too. It's in your side note here, your marginal note, low d high minus high d low, and they just left off the last part, over low low. Okay. So, you can certainly do the proof. It's not that bad, but it takes a little more explanation than just what it looks like there, I think. Okay, so let's do example 4. I don't think we have a slide for example 4, so let's do it here. Any questions on this before we get started? Okay. Compute the derivative of this function, f. Okay, it's x over 1 plus x squared. What is the derivative of that? F prime of x. You tell me, how do we begin? Someone make a guess. There's the rule right down here. If it's for Jeopardy, the buzzer would have already gone. Oh, never mind. Go ahead. Say that again.
So, like, the x on top will stay the same?
The x on top, no. Okay. What's the rule? Low d high. Low here is your denominator. 1 plus x squared times the derivative of the numerator, which is neither one. 1! Okay, 1. Derivative of x is 1, right? Exponent 1, coefficient 1, 1 times 1, reduce the exponent by 1, it becomes 0. X is 0 is 1, so it's 1 times 1 times 1. Okay, 1. Okay, next. Minus x times. Okay, it's derivative of that. Okay, derivative of 0 is 1. Okay, got it? I mean, the derivative of 1 is 0. Yeah, sorry. Say again? Where'd you get 3? 2 what? Huh? 2x. Okay. All right. You see why? Derivative of x squared is 2x. Okay. Over what? Squared, exactly. Ooh, what a mess. Okay, let's see if we can clean it up any. Okay, I'm going to remove that parentheses because it's really not doing anything for us. I put it there just so you'll see that's the denominator, that's your low. So let's see, clean that out. It wasn't doing anything for us. Okay, and let's see what else we got. You got a 1 plus x squared minus 2x squared over Let's just leave that alone. 1 plus x squared squared. Okay, can we simplify that numerator any? One. Second. It's a minus, isn't it? Plus x squared minus 2x squared. Add those two together and you get a minus 1x squared. Okay? Over 1 plus x squared squared. Now at this point, I always stop to see, can I simplify anything? Okay? Now I know I can factor that denominator into 1 plus x squared times 1 plus x squared, right? Okay, that's what it means. I can simplify the numerator into 1 plus x times 1 minus x. But all that factoring and simplification gets me nowhere. It doesn't get any simpler. There's nothing you can divide out, so that's your answer. Okay? Always check and see if you can simplify the answer. Let's see what they got. 1 minus x squared over 1 plus x squared squared. Perfect. Good for them. Okay? Ready for next? Okay. All right to erase? Everybody got it? Okay. Let's do example 5. d by dt, they're doing the various notations. This is called the Leibniz notation. d by dt of e to the t. I say t and write 2, as if t for 2, but 2 for t. No. E to the t over e to the t plus t. How would you take that derivative? Okay, the denominator, which is low e to the t plus t times e to the t, which is the derivative of the numerator, because e to the t is such a pretty function. Okay, then what? Minus numerator e to the t times e to the t, is that what you said? Because that is the derivative of e to the t. I couldn't hear the last part. Plus 1. Derivative of t is 1. Derivative of e to the t is e to the t, but the derivative of t is 1. And this is all over e to the t plus t squared, the whole thing squared. Very good. Now let's see if we can simplify, especially that numerator sum. All right. Going to have to distribute first, so let's do that. What's e to the t times e to the t? E to the 2t, yeah, e to the t squared, which is the same as e to the 2t. Next part of distributing. You did first times what? Yeah. A little louder. Plus t e to the t. Fantastic. Next. Minus, good. E to the 2t also. And minus e to the t. Everybody agree? E to the t? Agree? Okay, it rhymes. Okay. And what's in the denominator? Let's just leave it like it is. E to the t plus t squared. Anything we can do to that numerator? And what do you get? Oh, they add to 0, don't they? Okay. So now we've got t, and you know what else I want to do? I want to go on and factor out an e to the t. Can I do that? Is that all right with y'all? Because both of the remaining terms have an e to the t in them, right? So let's factor out e to the t times, what's left? T minus 1. Okay, got it. That didn't do me a bit of good, did it? Okay. But it never hurts to try. But nothing will divide out in the denominator, so e to the t plus t squared. So you could have left it without factoring or d. It's just not a bad idea to see if it'll work. And they did factor, but they put the t minus 1 in front of the t, e to the t. That's up to them, over e to the t plus t squared. So we got exactly the same thing, except written in a different order. Now, again, if this had been a homework exercise in WebAssign or some of those things, if you'd have put this one and they were only that one, it tells you you have a wrong answer, and you do not. It is a correct answer. So I don't really care for WebAssign or any of those other packages like that. But if you want to have that as a help, now they do have good tutorials and things like that. If you want to have those, I'll certainly do it, but then you have to figure out how to use it, because I'm not going to make assignments on it. Okay? Everybody okay with that? Can I erase it? Okay. Let's go to example 6. Oh boy. This one is not just calculate a derivative. It says find the tangent line to the graph of f of x is equal to 3x squared plus x minus 2 sorry, minus 2 over 4x cubed plus 1. Okay, it says find the tangent line to that graph. It's got to give me a place. Oh, there it is, at x equal 1. How would you proceed?
We plug in first, x.
Plug in, you mean x equal 1? Okay, and then you'll get a number, right? Okay, and what do you do with that number? It's not a bad idea, but I just want to see fuller where you're going with it. Okay, a little louder.
You solve it first, then plug in x equals 1.
Okay, solve it first. What do you mean by that?
Find the derivative.
Oh, find the derivative. Okay, I can get that. What you were saying before, though, is good. Now, okay, I don't know if this helps you or not, but it helps me to figure out where we're going. Okay, what does it say here? Find the tangent line. So one thing you might want to do is write down your equation for the tangent line. What do you think this is going to look like? Any ideas? What's that tangent line going to look like? Equation for a tangent line. That's what it says. Find the tangent line. There it is. No, never mind. That's not what it is. No, okay. What is your answer going to look like? Always good to have your answer in mind. It's a good idea. I mean, what Juan said, both of his suggestions were great suggestions, but what are you going to do with them? So what were you going to say?
Ordered pair.
Ordered pair? A tangent line is not an ordered pair. That's a point. A tangent line is a, okay, it could be written that way. Probably the easier way to write it, at least in the intermediate. I think in the final term, say again? Okay, say this again. Well, usually do it, yeah, let's try it that way. Y minus Y1 equals M times X minus X1. Okay, ultimately I think we will get down to MX plus B, but that's the place to head now. Now identify for me, you tell me, what is this Y? A variable. It's a letter. Leave it alone. What is Y1? It's what? It's what? Well, it's a Y coordinate of a point on the graph. And I don't see any Y's up there at all. So let's back off. What is that Y when you are dealing with that problem here? This is what I tell my students. No, Y is not a constant, it's a variable. Y1 is a constant. What is Y? There's no Y's up there. Where do you see a Y up there? F of X is always Y. Remember that. If you get that, you've got functions down pat. So the Y is going to be what that F of X is. I prefer it as Y, okay? So just remember, that's what that is. Now, what's your Y1 then? Say again? Well, it's not a point, it's a coordinate. Half of a point, you know, so you get half a point on that one. Okay, no. It's what? Not yet, okay? Okay, I feel like we've gone from knowledge to guessing now. Am I right? Never mind. Okay, Y1, as someone said at one point, is a number. It's the number for Y, what you get when you plug in X equal 1. Exactly. And here's Jasmine. Good to see you.
Did you get my email?
No. Well, I mean, I may have gotten it. I haven't seen it.
Okay.
Okay, that's fine. Just good to see you. Okay. There you are. All right. Now, back to this. We're on page 138. This is chapter 3, section 3.3. And by the way, did you get the first test?
Yeah.
You did? Okay. Well, then I just happen to have it right on top. Did everybody else in here get the first test? Anyone who did not? Okay. Okay. We're finding the tangent line for this function. Okay? So the first thing we did, one of the first things we did, was figure out what the tangent line is going to look like. Y minus Y1 is equal to M times X minus X1. That's a good working definition of that tangent line. Y is the variable that is f of X. Variable. Okay, not a number. Y1 is a value for Y, or for f of X, when? When you plug in 1. That's why 1's idea, first idea, was a great one. But I just wanted to know what he was going to do with it. So one thing we're going to do, what 1 said, is plug in 1. Okay. And what will that be? F of 1. That's, by the way, going to be Y1, just by happenstance, the 1's are there. What would that be? Pretty easy to do. Help me, help me. Not that hard. This is the easy part. It's what you wanted to do. Do it. Okay. It's what? 8. Okay, you got 3 plus 1 is 4 minus 2. Yeah, that is a minus. Sorry about that. 2 over 5. Perfect. 2/5. That's your Y1. Okay? Whew, we got somewhere. Next question. What's the M? Okay, I'm going to start filling in the blanks while we got it. Y is a variable, leave it alone. Minus 2/5 is equal to, now what's the M? Someone tell me what M is. Ah, very good. M is the slope of the tangent line, which is the first derivative. That's why one second idea was a good idea. Take a derivative. Okay? F prime of x is then what? Second? Have an equation?
Are you asking for an equation?
I'm asking for you to take a derivative of f. There's f. Take a derivative. N. Never mind. Oh, okay. Okay. 4x cubed plus 1. Good start. Times. Second. 6x plus 1, derivative of the top, low d high, minus 3x squared plus x minus 2 times, second, 12x squared. That's the numerator. What's the denominator? Four x cubed plus 1 squared. Got it. Okay. Now, any of you want to do a lot of simplification on that? You could, but what are we going to do with it? We want the slope at that point. So you can simplify first if you want to, or plug in the value if you want to. Which you want to do? I'd say plug it in. So f prime at 1, when x is equal to 1, would be, what's that first one? Help me, help me. Not that hard. 5 times, second, a little louder, 7 minus, okay, I can do that part, okay, 2 12. Okay, one thing I love about plugging in ones, you just add the coefficients, right? 4 plus 1 is 5, 6 plus 1 is 7, 3 plus 1 minus 2 is 2, 12. Okay, real easy to square 1, cube 1, take the square root of 1, take the cube root of 1, it's 1. Okay, we like 1, don't we? Never mind, okay. Divided by 25. 5 squared is 25. So let's clean that up a little bit. What would that be? 11. Second? 35 minus 24 over 25, which is 11 over 25. There's your slope. 11 over 25. Times, the rest of it's pretty easy. X minus 1. Good. We like 1, don't we? Okay, never mind. All right. All right. Now, the rest of it's algebra. It's a little messy, but it's not too bad. In fact, we probably aren't going to wind up in slope-intercept form, because this one just to get rid of those denominators, I think will be a little better. So let's rewrite this as y minus 2/5. That answer, by the way, is a perfectly legitimate, good answer. You get full credit for that answer. There's nothing really you can do to simplify, but I doubt if that's how they have it in the book. So let's see what they're going to do. Is equal to 11/25 x minus 11/25. Do you buy that? You just distribute the slope across the binomial there. Okay, now what I would do next is multiply every term by 25 just to get rid of the denominators, because I don't really like denominators that much. They're fine, but I don't really care for them. Okay, so let's multiply everything on both sides by 25. And what do you get? 25y minus over 5. 10. I like to do 5 into 25 as 5 times 2 is 10, but either way you want to do it, is equal to 11x minus 11. I kind of like that, okay? So let's, just for funsies here, I think what I want to do is move this to that side, move the variables to one side and the numbers to the other side. So let's subtract 25y from both sides. You don't have to do it this way, and add 11 to both sides. And that would give you 11x minus 25y is equal to 1. Okay? Now, that may not be the way they formed their answer, but to me, that's one of the simplest ways to do it. If you did it the other way and got it in slope-intercept form, you have some adding of fractions and stuff like that to do, and it's doable. Let's just do that while we have it here. Pick up the wrong pen. When you had it in this form, y minus 2/5 is equal to 11/25 x minus 11/25. To get it in slope-intercept form, all you do is add 2/5 to both sides. But over here, I'm going to be judicious in adding that 2/5. I'm going to add it in terms of 25ths. So that's going to be 10/25, isn't it? Isn't 2/5 the same as 10/25? 5 times the numerator, 5 times the denominator. That makes this easier to add, right? So these go away. Y is equal to 11/25 x minus 1/25. Okay, that slope-intercept form, this is what some old texts used to call standard form. I don't find anything very standard about it, except it doesn't have any fractions in it. This form's perfectly fine too. This is point slope form, slope-intercept form, or the old standard form. Let's see which one the book landed on. They wound up in slope-intercept form. Oh, they put it both ways. They said either this form or that form. They didn't take it one more step. Okay? So you see one's idea of plugging in the 1, yes, that's part of the problem. But the good idea is get your overall picture. Where do you want to go? To get an equation of a tangent line, this is what that equation is going to look like. You plug in x equal 1 to get y1. You take a derivative to get m, and you plug in x1 to get your x1. Okay, that's the easy part. So taking a derivative was necessary, plugging in was necessary, but also plugging in after you took a derivative was necessary. Good deal. Any questions on that? All right. How about example 7? I think it's right here. Power delivered by a battery. The power that a battery supplies to an apparatus, such as a laptop, depends on the internal resistance of the battery, like the ones you threw all over the floor, right? Okay, no, okay. All right. For a battery of voltage V, blow this up for just a moment, just so you'll maybe see it a little better. And by the way, I don't know if any of you have had physics before or anything else that ran into electrical stuff. Usually a battery is represented by, in a diagram, as a long bar and a short bar, with the long bar being the positive pole of the battery, the short bar being the negative pole. Most of the time you don't see the internal resistance specifically placed here like this, okay? And I'm not sure I would have placed it on top. I probably would have placed it on the bottom. It doesn't matter where you place it, but that's the internal resistance of the battery. Most of the time you don't even concern yourself with that, but that's part of this problem, okay? So that's what that stands for. Here's your battery with the voltage and the internal resistance. And then over here you have an external resistor, a light bulb, a heater, it was a laptop. So the laptop's over here, okay? That's your resistor, okay? So here's an apparatus of resistance R attached to a battery voltage V, but that battery also has an internal resistance, little r, which is usually very small, is why we usually ignore it, okay? But for a battery of voltage V, as shown in this picture, internal resistance R, the total power delivered, and I'm not going to drive this for you, but we could, but most of you going to wind up taking physics or not? Yeah, when you do, you'll run into a formula very similar to this then. May not deal with internal resistance, but you'll do the other. But anyway, they just give you the formula here. That power, so let me shrink this back, the power P, measured by the way in watts, okay, is equal to V squared over R. Now that's capital R, the external resistance, the laptop resistance, divided by the sum of the external resistance plus the internal resistance squared. Boy, it looks like we're going to have some fun times with this, because the first question they asked, the A part here, says find dP dr. dP dr. And that, by the way, was a capital R. Okay? In other words, how does the power change as you increase or decrease that external resistance? So this is the rate of change of the power with the change of that external resistance. Not the internal. The internal is pretty much fixed. That little r is a constant. Okay? The capital R, you can do some varying on that, and then you're going to change that. Now, I don't even know what unit you would use for this. Actually, I do, but we'll worry about that later. I don't think this is a math book. They're not going to care too much. Okay? So calculate dP dr, assuming that the voltage and the internal resistance are constants. So take me to town here. How do we do this? All right, here's team. All right. Wound up being pretty good attendance today, and I guess a couple of you have come in since I made this. Sorry. For those who got here early, sorry you have to hear it so many times. But the vice president sent an email sometime last week, and when I read it, I wasn't at my computer, so I couldn't print it off. And this morning, I forgot to print it off. So I'm just going to tell you what it says. I'm supposed to read it to you, but this is the essence of it. If you or anyone else you know hasn't paid by 5 o'clock today, you're going to get removed from the roll. Most schools would have had you out of here well before now, but we're pretty lenient. Maybe that's a good term I wanted to use there. Lenient, or I don't know what else. And we've allowed you this long, almost half the course, without paying if you haven't paid or haven't paid completely. So if you have it, please, and if you know of any other students who have it, please get them to go by the business office or somewhere and work out something. Let them know that you are planning to pay, this is what you're waiting for, you're going to do something, you want to pay a part of it today, do something to let them know that you are in the process of paying, so you won't be dropped from the roll. They may drop you anyway, but usually if you've made some sort of good faith effort, they'll put you back in, which is sort of a pain in the neck too. But it's better than being removed completely. So, just wanted to let everybody know that because I announced it early, and since you were here, I didn't know if you were going to go back and listen to screencast or YouTube, but it's going to be late enough in the day, it'd be fairly late, hard to get it done by then. So let's do dp dr. Okay, where would you begin? You tell me. Help me, help me. Okay. R plus, capital R plus little r squared times V squared, right? V is a constant, right? R is your variable here, so that's just some constant times R. Constant times R, derivative of that would just be the constant, right? By that? Okay. Next. By the way, this is example 7 at the bottom of page 138 in section 3.3 of chapter 3. Next. Minus R. Where is that coming from? So I'll know it. No, it's okay. Here's the simple thing on it. Low d high, that's what we did here. We wrote down low, then we took the derivative of the high numerator, and that was just v squared. Now, again, d and little r are constants. So this is low d high minus high, which is v squared r times say that one more time. Okay, yeah, 2 times big R plus little r to the first power, right? That was absolutely correct, okay? Divided by R plus little r squared. Wouldn't that be to the fourth then? Because your problem was squared, and then when you take the derivative, you square that, okay? Now, what a mess, okay? Let's see what else they say. Calculate, assuming that capital V and capital R, I should have written that down, V and little r constant. Okay. Now, that's a kind of messy form, isn't it? So let's see if we can sweeten that up a little bit. That will be, I don't know how far I want to go on this. We'll start with it. V squared capital R. No. I'm all real tempted to just leave it in that form. Because I sure don't want to multiply all that out. Do I? Let's just leave that part like it is. Capital R plus little r squared times V squared minus, I can simplify this a little bit. V squared is a constant, capital R is a number, variable, 2 is a constant, and capital R is a thing again. So let's get all those together. That'd be 2V squared capital R squared, right? Everybody buy that as the first term? And the second term would be those first 3 times little r. So that would be a minus again, let me put the 2 out front, 2v squared little r times capital R. Okay? I'm not sure that's a lot better, but it just got rid of one parenthesis anyway. Two parentheses, in fact. Okay? And that would be over R plus little r to the fourth power. Now, I think I do have to multiply that. I was resisting that, but let's do it. What is capital R plus little r squared? Can you do that off to the side here? Capital R plus little r squared. Help me, help me. This thing right here. What is that? Square a binomial. It's not that bad. Capital R squared plus 2 capital R little r. I should put little r first, but it's okay. Plus little r squared. That's it. Okay, let's multiply that by the v squared. Okay, so that'd be v squared capital R squared minus 2v squared little r times capital R, right? It's just v squared times that, okay? Plus capital V squared little r squared, right? That's just distributing this across all three of those terms, right? Okay. Minus 2v squared capital R squared minus 2v squared little r capital R, all divided by capital R plus little r to the fourth. Okay, can we do anything with this? Like terms here, there's a minus v squared capital R squared, right? And here we have, say again? V squared little r capital R. And, oh, wait, we missed, no, I'm sorry, we didn't, okay, plus v squared little r squared, okay, all over r plus little r to the fourth. I'm not sure that helped a lot, but it made fewer terms, a little bit neater to look at, okay? So, let's see if that's what they got. Oh boy. All right. All right. Rather strangely here, they left the derivatives in here. And it does make things look a lot simpler. dp dr All right. Have I done something stupid here? Let me hold off just a minute here. the denominator times derivative of the numerator, which is that, okay? Okay, plus the numerator times, minus the numerator times the derivative of the denominator, which of course is that, okay, over denominator squared. I think everything we've done is correct now. All right, okay, let's do this now. In the numerator, we have a v squared everywhere. Okay, so let's factor out a v squared. Okay, ha, I know what they're doing. Okay, I think I do anyway. And then we have yeah, let's factor out the v squared, which I probably should have done at the very beginning. Okay. And that would be times little r squared, that first term. And what we have next is minus capital R squared minus 4 little r capital R over r plus little r to the fourth. I don't quite see how they... Oh, I'm sorry. This is what they've got. I'm sorry. They just left it in terms of... I can't tell you why they did this, but they left it in terms of that. Okay. Our answer is perfectly fine. It is correct. If you'll see there, there's our v squared. Well, if you go back up here, this is exactly what they've got here. Factor out the v squared in that top term, and you have r plus r squared, okay, minus r times dr, and why they... Okay, if you go to this very first term up here that we did, factor out the v squared. This is how they left it, and I don't know why. Times capital R plus little r squared minus r times and then they did just dr. They left it without actually taking derivative, but what we did was correct. 2 times r plus little r, okay, over r plus little r to the fourth. They just left it like that. In fact, they didn't even take it that far, but they left it there. Now, I don't know why they chose to. Okay, the B part says, where in the graph of P versus R is the tangent horizontal? Now, what makes a tangent horizontal? What's true about a horizontal tangent? What's true about a horizontal tangent? Any horizontal line. What's zero? The what? Not the x, not the origin. What's true about every horizontal line, wherever it is? The slope is zero. which is the first derivative. So basically then what we do is set this equal to 0. Okay? This is our first derivative. Okay? And set it equal to 0. And oh, I'm sorry. Now that I look at their answer, it's not nearly as wacko as I thought it was. Okay. They did carry it further. They took several stops in between. Let's take our answer that we got here and do a little bit of messing with it. Okay? Certainly the v squared's out front. Okay? And what we have then is a r squared, little r squared, minus a capital R squared plus 4r capital R over capital R plus little r to the 4th. Okay. Now here's what they're going to do. If you'll notice here, you can factor out an r out of this term. Okay? Yeah, they do. I mean, what we've got is exactly, it's pretty close to what they've got. I swear. They've just really messed this up some. But anyway, I'm going to have to clear. I don't have enough room to write anymore. So I'm going to clear this out of the way and pick up where they left off, which is about the same place we will. Okay. Here's what they got for the d, p, d, capital R. Okay. It's going to be the v squared, and this is the part r minus capital R over r plus little r cubed. Now what happened there was r plus little r from that numerator we had that cancels one of those out, and this is a simple way to write that answer. So this is the end result of what we were getting toward. Okay, so what we do here is we want this to be equal to 0. Okay, that's where this is the slope of the tangent line. Of course, this is a constant, so we're not worried about that any. We're not getting rid of it, but I'm just saying it's a constant, so we're not worried about that. So the thing that's going to make this 0, the only thing that can make this 0 is if the numerator is 0. And v squared can't be 0. That's a constant. The voltage is voltage. It's not 0. Doesn't matter what the denominator is. That's not going to make the value 0. What makes the value 0 is that little r equal capital R. Right? That's where that goes to 0. So that means that if the only resistance you had in the problem, or if the resistance in your problem was exactly equal to the internal resistance, that's where your slope is equal to 0. Okay? And that's what they're getting at. That capital R would equal little r. That's the only place that's going to be at 0. So let's move on here. Sorry that I took too long on this problem. All the r's thing. Now, again, I cannot for the life of me figure out why they wrote this the way they did. Now, the first thing they did was really smart. The v squared is a constant, bring it on the outside, leaving you only capital R's and little r's here. So the derivative of this is this times derivative of that, which is 1, minus this times derivative of that, which they just left written like that, which is bizarre, okay? Divided by this thing squared, which is that to the 4th, okay? So again, I wish they showed this on the same slide, but they do it on the next slide. And if I had realized they had all this, I wouldn't have done all the writing, because it would save me some writing. So they then do this, just this. Remember, this was the that last term, d by dr. You did it correctly. You did it absolutely correctly. But what they chose to do is expand this out and then take the derivative, which is fine. You're going to see it got the same thing we did. Okay? They expanded this out, r squared plus 2r, little r, capital R, plus r squared, little r squared. And this would be 2r plus 2r, because the derivative of r is, when you take the derivative of this, you just get 2r, and then that's 0. So why did they even do that? So this is just 2 times capital R plus little r. That's the place where they wound up with r plus r in the numerator. If I had done, we wound up with that, but we just sort of mucked it up with the v's in there. Okay, so once you have that, okay, you had, let's go back here, that just had 2r plus little r. Okay, so let's go back and look at this one again. Okay, keep hitting the wrong keys. Okay, now you see this term has an r plus r in it. This term, when you take the derivative of that, it has 2 times r plus r. So this has r plus r in it. So they factor out this r plus r with one of these r plus r's and canceled one of those out. So that's where they got the r plus r cubed in the denominator. Okay? This stuff makes no sense, but if you, the way we did it was fine, except I had all those things wadded up and you didn't see it as easily. This way, you, if you left off the d by drs, that would be even nicer. Okay? But that's how you lost that. Okay? And got, okay. Now, when you get all that together, again, I wish I'd have done this rather than writing it all out. Okay, the v squared's out here. This had a r plus r squared minus 2r times r plus r over this. So one of these r plus r, that r plus r, cancel out one of those. So you're left with a v squared r plus r minus 2r, that's all that's left here, over r plus r cubed. And when you do this, capital R minus 2r, that gives you just a minus r. So you got little r minus r over that. So that's how you get your dp dr. That is, except for their drs that they had in that middle step, this is the neatest way to do it. Okay? So we got what dp dr is. Then when you get, where is it horizontal? It has to be where capital R is equal to little r. And that's exactly what you get. Capital R equal little r, that's where your derivative is 0. So, the graph of power versus resistance, when you have no resistance, which you never have, you have no power, okay, because that power formula has a resistance there. But then the power goes up very steeply until you get to the only resistance you have in that circuit is little r. I'm sorry, so the external resistance is equal to that. That's where you have maximum power. Then after that it falls off because the resistor is using some of your power. The laptop is. Up here you're just basically charging, you know, up to here, and then after that, so your maximum power would be right there where your external resistance is equal to the internal resistance. Sorry that took way too long. Okay. Should have blown this up. Okay. Now, I think that is the last slide in the section. Now, do y'all want to do preliminary questions, yay or nay? Huh? Nay? Okay. So we'll go straight to the homework exercises. Do any of the odds 1 through 5, any of the odds 7 through 11, either 13 or 15 or both, And then any of the odds between 17 and 37. There's a whole bunch of them there. I would do more than just one. Do several of those. Then do any of the odds, either 39 or 41 or both. And then any of the odds 43 through 53. You choose. Okay? I would do at least one of those and possibly more if any of them look particularly interesting to you. While we're here, if you'll notice, question number 53 refers to the witch of Agnesi. Agnesi? I don't know how to pronounce that. After the Italian mathematician Maria Agnesi. Now, they weren't claiming that she was a witch or anything. The strange name is a result of a mistranslation of the Italian word la vesiera, which means that which turns, and they mistranslated it to a witch. Okay, so not a very nice thing to do, but I think you'll find if you did some research on this, Maria Agnesi was one of the first well-recognized and respected women mathematician in history, okay? Maybe not the first, but one of the first, okay? And then this curve that she discovered and wrote about, and she, by the way, she also who wrote one of the first books on calculus. She gave this, I think, as an example in her book. So if nothing else, you might find a paper topic or two in there if any of you are interested. Okay. The others, those further insights and challenges, if you feel really like you need more challenge, go for them. The odd numbers are in the back. Any questions? Let's move on to 3.4. Sorry that took too long on that last problem because I got sort of bogged down in some gritty details that I could have avoided if I simplified a little bit. Where is it coming? You would think PowerPoint hadn't already opened something. There it goes. Okay. From current slide. Now, we're revisiting something we've already talked about, okay? And this is rates of change, okay? If you remember, if you had pre-calculus, you probably talked about average rate of change in pre-calculus. I know our students here at Lawson do. But let's look at rates of change. Recall that the notation for the average rate of change of a function, y is equal to f of x, would be dy dx. I'm sorry, delta y over delta x. Average rate of change of the function y as a function of x would be the change of y over the change of x. That's also called what? Average rate of change would be the slope of what? The secant line between 2 points. x1, y1, and x0, y0, and x1, y1. So this would be y1 minus y0 over x1 minus x0. Change of y over change of x. That's your average rate of change. Okay? Seems like we're almost going backwards here. Okay? Now, if you're going to instantaneous rate of change, and most of the time we'll leave off the term instantaneous, but when we do this, then that becomes dy dx, right? Instantaneous rate would be as x goes to 0, delta x goes to 0, then that becomes a derivative, dy dx, and that would be the limit of your numerator, over your denominator, which takes us right back to where we were. It seems like sections ago, okay, when we were doing this at the very beginning. So the instantaneous rate of change, which for now, for the most part, we're just going to call rate of change, That's the derivative at x0. That's the limit of delta y over delta x as delta x gets close to 0. That could also be written as the limit as delta 1 is approaching delta 0. Delta x1 is approaching delta. That's the limit as x1 is approaching x0. That's your delta x1 to 0 of alpha of x1 minus alpha of x0 over x1 minus x0. Remember back when we did limits, we said two ways to write it, this way and with h's. And for a while we've been dealing with the h's. If h approaches 0, then we had change of y over h, and the y was defined as alpha of x plus h minus alpha of x over h. Same thing here. This was the other way. In fact, this is the way we did first, I think, when we did limits. Okay? But this is exactly what we've got. It's another definition of a derivative. I mean, it's just written in a different limit form. Okay? And I think we've done this with the tangent, with the secant lines going to the tangent line. How many times? You know, over and over and over again. But this is what we're talking about. Average rate of change between 2 points, x0 and x1. Okay? Then, if it was here at x0, y0, and up here at x1, it was x1, y1, then the average rate of change is the slope of the secant line between those 2 points. Where this is your delta y, that's your delta x. So again, going back over all this stuff we've done before, and then as we get x1 get closer and closer to 0, that secant line, as x1 gets closer and closer to x0, the secant line crawls back down this line, this curve, getting closer and closer until finally, as x1 approaches x0, you have the tangent. Same thing we've done repeatedly. Okay? Average rate of change is the slope of the secant line. The instantaneous rate of change is the slope of the tangent line. Okay? Why they did put this on the same graph, I'm not sure, but they have before how it is. As you let the x0 get closer, x1 get closer and closer to x0, that secant line gets closer and closer to d. And the limit of it is the slope of the tangent line. The instantaneous rate of change at x0 is the slope of the tangent line at that point. Same thing we were doing in the last section, okay? Except we weren't calling it average rate of change. And again, they talk about how they like the Leibniz notation, which is, of course, good. Nothing wrong with it. This is, I think, example 1. It says that table 1 here, I'll blow this up so you can see it a little bit better. Okay, table 1 here contains the data on the temperature, capital T, that's the right-hand column, on the surface of Mars at Martian time, little t. So this is Martian time, little t. And these are data from the Mars Pathfinder mission of July 1997. I'm trying to remember if this is still there or not. We have some rovers up on Mars that have been sending data for years and years. I can't remember if Pathfinder is still sending data. They may have finally died, but 2 others I think are still sending. Okay, it says calculate the average rate of change of temperature T from 6:11 a.m. to 9:05 a.m. So from this time, whoops, 6:11. Let me get my pen back. Okay, from 6:11 to 9:05. We want the average rate of change between those, average rate of change of temperature between those times. So what would that be? Average rate of change. Again, this is stuff we've already done. How do we do that? If it's average rate of change, it's delta temperature over delta time. Strange they have the same first letters. So temperature is capital T, time is little t. So what's your change of temperature over that time? Okay, always final minus initial, negative 44.3, these are degrees Celsius, minus a minus 71.6 divided by 905 minus 611. Okay, that's your average rate of change, right? Now, a little bit of mess here. The numerator is perfectly fine. It's got negatives in it, but what would that come out being? Any of you do that? 27.3. 27.3. Those are degrees Celsius. I didn't put them in originally, but I did here. This next part, let's sit down and do this separately. 905 minus 611. Now remember, we're dealing with hours and minutes, right? So 1 from 5 is 4. You can't do 1 from 0, so you borrow an hour here, leaving you 8 hours here. Add that here. How many minutes is an hour? It's 60 minutes, right? 60. Well, we already dealt with the 0. So this gives you a 5 here, and this will give you 2 hours and 54 minutes, right? Did I do the subtraction right? Yeah, looks pretty good. Now, we want that in minutes, don't we? So 2 hours is 120 minutes, plus 54 minutes is 174 minutes. So divide this by 174 minutes. Okay? That will give you what you're looking for. What would you get? .15 degrees Celsius per minute. Okay, that's how much the temperature is increasing from 6:11 in a Martian morning to 9:05 on that same Martian morning. It's going up about 0.15 of a degree per minute. Okay? Silly me, for some reason they wanted it per hour. Okay? You could go the other way. If you wanted it per hour, this is 2 hours plus 54/60ths of an hour. Well, with your calculator, tell me how many hours that is. 27.3 degrees Celsius over 2. What's 54 divided by 60? To maybe 2 digits. Say again? 0.9. Okay. And then divide 27.3 by 2.9. This is hours this time. That would be, all those do that in my head, 3. What? Oh, I'm sorry, 9 point. Yeah, 9 point. I wasn't thinking clearly. 9 point what? 9.4 degrees Celsius per hour. Okay, going up about close to 9.5 degrees per hour. Degrees Celsius per hour. Okay? Now, the rate of change is the derivative dt, that's d capital T, d little t, which is equal to the slope of the tangent line through the point 228 negative 22.3. Oh, I'm sorry. That was all for this problem. Let's go to the B part. Here now we have a graph of temperature versus time. And this would probably be pretty close to what you actually get if you had, say, and I was on an ammunition ship, and there were some holes in the ammunition ship had really sensitive ammunition in them that you really did not want to get too hot. So we had a strip chart recorder there that measured temperature over time, and we had a watch. We went around and checked all the ammunition holes in the whole ship. It's quite stair climbing, but this one he actually would check the strip chart recorder and probably pulled it off every hour that he went by there to make sure the temperature hadn't spiked too much in that hole. They didn't care whether our rooms were air conditioned. That room better be air conditioned, or that space that better be air conditioned. Otherwise, the whole ship makes a big hole in the water and cares whether our rooms were air conditioned or not. We weren't there anymore. Okay, so this shows temperature variation on the surface of Mars on July 6th, which was the they didn't tell us what date it was, but this is some date. And at midnight, that means the sun was furthest from the planet was turned away. It just continued to drop and drop and drop until the sun rose. It looked like about 4:50 that morning, and then the temperature started rising and then going down again. Okay? Now, what they said here, the B part says use figure 3, which is this, to estimate the rate of change at T is equal to 2:28 p.m. 12:28 p.m. I can't read. 12:28 p.m. Oh my word. 9:36, 14:24. You have to take their word for it. It's that point right there. Okay? Now, here's how you do an estimate there. You draw your best guess of a tangent line there, right? Now, they told you this point. They told you at 12:28 it was negative 22.3 degrees Celsius, right? Draw your best guess of a tangent line there, okay? And that's as good a guess as any I see. Well, then come down here somewhere that you see you can estimate a time and a temperature. Now, you might want to carry this on down to here, but they don't have the tick marks here. They do have tick marks here. And I'm guessing there's 1, 2, 3, 4, 5, 6, 7. I'm guessing there's 10 in between there. I can't count them. They're too smudgy here. But anyway, at 4:48 exactly, on that tangent line, you would have been at minus 50, maybe 2 degrees. They made the dot so big, it's hard to say. So you have another point. So from that point to that point, estimate the slope of the tangent line. And I don't know what they used. Did they use 51? They used minus 51, which they estimated. Now I'm going to have to go back. Estimated this point. I can tell you the time exactly, 4:48, and the tangent line there would have read, they said minus 51 degrees Celsius. Okay, so again, do the slope of that one, which is rise over run, negative 22.3 minus a negative 51, so minus 51 divided by, and they told you the time there, we read the time here, 12:28 minus 4:48. And based on what they did last time, that would be a plus 50 minus 22. That's going to be plus 51 minus 22. A minus 28 0.7. Someone check my math here. I'm doing it in my head. And based on what they did before, now what this is a 0.4 here, so you don't confuse it with 4 in the afternoon. So that's going to be, and again we do 1220 minus 448, and again we're going to have to borrow an hour here and make that 11, and add 60 to 20 and you get 80. 8 from 10 would be 2, and 4 from 7 would be 3. Okay, and that would then be 7 hours and 32 minutes. Just a little more than 7.5 hours. So again, do 7 plus 32 over 60. So get your decimal form there. That's what? 7 point what? Anyone got it? 32 divided by 60. Not on the nose, is it? One more digit? 5.3? Okay. Now do that division and you get something a little less than 4, right? Negative 4. Second, negative 3 point. One more digit. 8.1. Okay. And let's see what they got. They rounded to negative 3.7. I'm not sure how they got that. Maybe they did their math right. Oh, yeah. No? Oh, they got 0.67. How did they do that? Well, maybe because they wrote the problem down right. Okay, I'm sorry, that was 1228, not 1220. Sorry about that. I can't read my writing. 1228. Someone should have caught me on that one. Okay, so that would be exactly that would be 88 minutes, so that would be 40 minutes. 7. So that would be 7.67. 7.67. Okay, and that would change our number. Negative 3 point. What they got. They rounded to negative 3.7 degrees per hour. Okay. Now, when you're using real data like this, that's about the best you can do. You don't have a function here you can take a derivative of it, so your best guess is to do your best estimate of the tangent line. You know the value here, and then find someplace back here where you can estimate a value. And if you cross one of these lines, you know that pretty closely, and then estimate the value here. So that gives you your data points, do your subtraction. You know, calculate the slope. Okay. Not exact, but it's best you can usually do. All right. Any questions on that? Now, okay. This, I think, is the next problem. Let me set it up for you. You all know this, right? Area of a circle. What is it? Formula. Area of a circle. No, that's the circumference of a circle. That's the area of a circle. Pi r squared. I always thought pi were round, but pi r squared. Never mind, that's dumb. Okay. Now, let that be an area of, it is the area of a circle of radius r. The A part here says, compute dA dr. In other words, how is the area increasing as you increase the radius at r equal 2, okay? And let's do it again at r equal 5. So we're going to do it at two different places, okay? Guess what we got to do first? Second? Not yet. You do this first. Take a derivative. What would the derivative be? dA dr, Leibniz notation would be, and surprisingly, it's exactly what you said before. What is it? 2 pi r. Because pi is a constant. It's just a number. Okay, it's a constant. R is a variable. Okay, so 2 pi r, 2 pi times r to the 1 power. Okay, now this is where we plug it in. Let's plug it in at r is equal to 2, and what do you get? Pretty easy. You don't need an actual number, just give me, wouldn't that be? 2 times pi times 2 would be 4 pi. And let's do it also at r is equal to 5, and that would be 10 pi. So the rate of change of the area as the radius is getting bigger, when it's a small circle, r is equal to 2, the rate of change is only 4 pi. When it gets up to r equal 5, the rate of change is 10 pi. So it's increasing much faster at a larger if the radius is increasing at the same speed, then the area is increasing much bigger. And they did actually, they did actually estimate this, and what would that be? 4 times pi is 12 point something another, isn't it? 0.57. And 10 pi, I can guess that one. That's 31.42, right? 3.141, yeah, something like that. 31.42. Clean that up some. Still pretty thick, okay. It's 10 times pi, okay. Now, why is dr dA larger at r equal 5 than it is at r equal 4? Same derivative, isn't it? If r is increasing at the same rate, the area is increasing even faster at that rate, because area changes as the radius squared, not directly as the radius. Okay? So yeah, that's why. I mean, several reasons there. Derivative dA dr measures how the area changes. And this next figure shows this. And it really is a good thing to think of it in kind of all these terms. A is equal to pi r squared. There would be the graph of that curve. Now again, they've expanded the r and contracted the area big time. They don't even put the scale on here. But you know, if this is 2 and this is 4 pi and this is 10 pi, this is something around 12, this is something around 31. So yeah, this scale, that's 31 and that's 3 or 4 there, you know, so really expanded scale. But your tangent line is here at 2, there at 5. The slope's really different, and here's why. R is equal to 2. When it expands just a little bit, that's your change of area, okay? When R is 5 and it's changed that same amount, R changes that same delta R, look how much more area has increased than it is here. Because any little strip of this is the same, there's just a lot more of that to go around, okay? So that's their description of that. So this is leading to the effect of a 1 unit change. Okay? Go backwards, kinda, to what we had before. And they're going back to the H notation. It doesn't really matter, like the others as well. But remember our f prime at x0. The real definition is the limit of this as h goes to 0. Okay? That was our thing. Yeah. So what we're going to do is take out the limit part and just estimate this. As long as h is small enough, this is not a bad estimate, right? Now, if h is really big, that's not going to give you a great estimate. But as h is getting closer and closer to 0, this is going to be a much better and better approximation of what the derivative is. It's not exact, it's an approximation. Okay? So, here's what we're going to do. Now, I admit 1 is not very close to 0, right? But if your scale for your x's was in the thousands, 1 is pretty close to 0. So this would be, if you have really big numbers for your independent variable, a change of 1 is not going to be much of a change. So therefore, this is going to be, okay, from the previous slide, remember we were dividing by h. Well, guess what? H is 1, so this gives it to you. So when you're dealing with really large values for your x's, a change of 1 is going to be approximately what you get as a first derivative. Okay? In other words, f prime of 0 is approximately equal to the change of f caused by a 1 unit change in x when x is equal to x. 0. Sorry. I'm clogging up inside. I don't know why. So let's talk about example 3, stopping distances. For speeds s between 30 and 75 miles per hour, MPH is miles per hour, not meters per hour, that's miles per hour. The stopping distance of an automobile after the brakes are applied is approximately, this is not the problem y'all have in your book. This is the cost, this problem here is cost of air flight. Let's go back and do example 3, which is not on the slide set. Sorry about that. For speeds s between 30 and 75 miles an hour. Okay? Okay, your speed is between that. The stopping distance of an automobile after the brakes are applied is f of s. That will be stopping distance. Why they chose capital F, I don't know. I think I would have done D or something else. But f of s is equal to 1.1 s plus 0.05 s squared. And this will be in feet. Stopping distance in feet. Okay? Now, what we want to do is pick your s equal 60 miles per hour. Okay? A part here says estimate the change in stopping distance if the speed is increased by 1 mile per hour. Now, why can we get away with h as big as 1? Look at the numbers we're dealing with, from 30 to 75. A change of 1 there is really small compared to 30, or certainly compared to 75, and certainly at 60, not far off. Okay? So what would be your estimate for this at there? Now, here's your formula down here. Your estimate the change in stopping distance, that would be df ds. Change in stopping distance. This is your stopping distance per time. and that would be approximately, and we're using capital F here, F of our x0 here. This is what we were calling x0. We're calling s0 now. Sorry, capital F of 61 minus capital F of 60. That would be approximately your rate of change of stopping the df ds. Okay? Well, let's just plug and chug and see what we get. This would be, someone with a calculator, 1.1 times 61 plus 0.05 times 61 squared minus 1.1 times 60, that would be 66, I can tell you what that is, minus 0.05 times 3600. Did you get all that? 1.1 times 61 plus 0.05 times 61 squared minus 66, that's 60 times 1.1 minus 0.05 times 3600. That's 60 squared. I can do that part in my head. What do you get this to be? (1.1 times 61 plus 0.05 times 61 squared minus 66 minus 0.05 times 3600. 7.15, and that distance would be in, that would be no, feet. They said this was in feet per let me see. Estimate the change in stopping distance. This is feet per mile per hour. In other words, for every extra mile per hour you would go, it's going to take you another 7.15 feet to stop. So from 60 to 61 miles per hour, it's about 7 more feet to stop. Okay? That's your change of stopping distance per change of speed. This is a distance, and this is a speed. So feet per mile per hour. Writing is not too good. Okay. Feet per mile per hour. Okay. That was the A part. The B part says compare your estimate with the actual increase in stopping distance. How do we get the actual increase? This was an approximate. What's the actual? Do your df ds. What would that be? Take your derivative. What do you get? Not that hard. Derivative of 1.1 times s with respect to s. Second? Wait, this one. Derivative of that. No. This is to the first power. 1 times 1.1 is 1.1 times s to the 0, which is 1. Derivative of a constant times a variable to the first power is that. the derivative of a linear function is the slope of the linear function. That would be the slope, 1.1, right? Next part, plus 0.1 twice times 0.05, 0.1 times s. But we're doing this when s is 60, so that would be 1.1 plus 0.1 times 60 would be 6, and that would be 6.7. No, 7.1. Sorry about that. Where am I? You're adding here. I was multiplying. Okay, 7.1. Right? And our estimate was 7.15. I'd say that's pretty good. And again, that would be feet per mile per hour. What is the increase in your stopping distance for every mile per hour? Okay? Let's see how they did it. And you know, it seems like to me they do this backwards. Every time I get here, I swear they've done it backwards. They say the actual difference in the stopping distance when you go to this formula, which of these is the estimate? Is that the estimate or is that the estimate? To me, this is reality. That's the estimate. And when they do it, they say the actual difference is this, and the estimate is that. And it just seems like to me they say it backwards. But either way, we've done it both. The actual change. Yeah. Yeah, I guess that's right. The estimate and the stopping distance is the first derivative. The actual change is the other. Okay. So now, have any of you taken any economics? I think you have. What's that? Macro? Did they ever talk about marginal rate of change? Do you remember that term? Yeah, that's what I usually think about economics too. Get it over with. No, I'm sorry, I didn't say that, did I? Okay. Now, when you read that, and they do it, especially in economics, marginal rate of change, that means what happens if you increase this just a marginal amount, a little bit, how is that going to affect the change? Which is exactly what we're talking about here. So, let C of X denote the dollar cost, including labor and parts, of producing X units of a particular product. The number X of units manufactured is called the production level. In the study of the relationship between the cost and production, economists define the marginal cost at production level X sub 0 as the cost of producing one additional unit. Okay? So the marginal cost would be the cost of X sub 0 plus 1 minus the cost of X sub 0. And as we saw, that's a messy calculation, just like we did here. where you did f of this minus f of that, that was a lot of calculation. When you take the derivative, which estimates that, really easy. So this is a far easier approximation than actually calculating those costs. Just take the derivative of it, okay? So here's an example that maybe some of you have actually experienced before. I think this is this graph here. Cost of air flight, okay? And for the life of me, I swear the airline companies, they've got to be crazy on some of this. They overbook seats, and then they offer people big bonuses to give up their seat. And it seems like to me if they, but I guess they haven't figured out, on most flights they're going to have a few seats short, and on very few flights will they actually overbook. But when they do, I guess they make up for it by giving them a lot more money. But I think, why don't they just stop selling tickets when they sold enough, the number of seats the plane will hold? They figure there's going to be some people not showing, but guess what? They've already bought their ticket. You know, it's sort of like what we do here. I don't know why we wait so long to, you know, say no, if you haven't paid, you're out of the class. And then the weird way we do it, but I don't know. I guess there's a reason for it. But here's the number of passengers, and here's the deal. Cost of air flight. Company data, and the graph doesn't show it, so in order to, well, let's talk about this. The slopes of the tangent line are decreasing, so the marginal cost is decreasing. If it's 150 passenger, the cost is going to be here, and to go up to 200 passengers, the cost will be there. This is per seat, per passenger. Okay? The total cost doesn't increase much for those 50 more people on the plane. Most of the costs are fixed costs down here. Okay? Whether you have no people on the plane, you're going to cost the fuel, you know, to fly the plane empty. This is the weight of the plane, the airport costs, the stewardess, the flight attendant. It's going to cost you a certain amount of money if you fly the plane with nobody on it. So when you got 150 people on it, it's going to cost that much. And 200 is only going to go up per person. It actually drops a little bit. Okay? The slopes, the cost of air flight, the slopes of the tangent lines are decreasing, so the marginal cost is a decreasing cost. Okay? So it's not going to cost you that more to add another passenger or another seat or something like this. So that's why they pack you in there like sardines. Okay. So company data, there's your graph. Company data suggests that the total dollar cost of a certain flight is approximately your C of X is equal to 0.0005 X cubed minus 0.38 X squared plus 120X, where X is the number of passengers as shown in this figure. Okay? Now, there's your actual cost. Estimate the marginal cost of additional passenger if the flight already has 150 passengers. So let's estimate the marginal cost. And what's the estimate for the marginal cost? C prime of X, okay? C prime at 150, okay? That's the approximate cost of adding one more passenger there. Well, what is your C prime? Do we need to take a little break? I know I do. Let's take a quick break. We'll come back to this. All right, we're doing example 4, cost of an airline flight. Here was the cost formula. It says estimate the marginal cost of an additional passenger on the flight if the flight already has 150 passengers. So we said the estimate for this will be the first derivative evaluated at 150. So let's first give me the first derivative. What would that be? So I think, let me go back and change this. Let's do f sub x, okay? It's our c prime x. What would that be? 0, 0, 1, 5 x squared minus 76 x plus 120. Okay? Evaluate that at 150. C prime of 150 would be what? Take some calculator on this one. 0.0015x times 150 squared minus 0.76 times 150 plus 120. What would you get? Say one more time. 6.05. That would be dollars per seat. Okay? In other words, it's only an additional cost of $6.05 per seat. Okay? Whoa, that's not what they got. Okay? I thought that seemed a little low. Okay? So I don't have a calculator on me, so I've, whoops, it's not erasing. Okay. Let's try it again. Okay, that's what the book got. Do you agree with it? Do you see why? Okay, what you say, 39.75? Okay, so one additional passenger is only going to cost the airline $39.75 to fly. So they sure want to fill all the seats they can. And I guess that's the reason they will pay passengers a whole lot if they overbook, if they will rebook. You know, doesn't seem like it would make sense to me, but that's what they do. Okay, estimate the marginal cost of that, and that's what they got, $39.75. Compare your estimate with the actual cost of an additional passenger. So what you have to do in that case is do C of 151 minus C of 150. So that's plugging in 151 to the original thing, 0.0005 times 151 cubed minus 0.38 times 151 squared plus 120 times 151 minus 0.0005 times 150 cubed, and then that would be a plus 0.038 150 squared minus 120 times 150. It's a lot more calculations. Anyone done it yet? In the book, they give the answer is 39.60, which is pretty close. I mean, our estimate was 15 cents more out of nearly $40, so pretty good estimate. Is it more expensive to add a passenger when X is equal to 150 or when it's equal to 200? Well, what we do then, we've already calculated C prime at 150, so do the C prime at 200. And this is almost easy enough you can do it in your head. Not in your head, but with minimal calculator. 0.0015 times 40000 minus 0.76 times 200. I could do that one in my head if I wanted to. Plus 120. Got an answer there? Huh? Yeah, that's what the book got to, doesn't it? Okay. $28. Okay, so yeah, it is, once you got 199 or 200 people on there, to add one more person is even less, because you see the cost is going down. The marginal cost, which is approximately that derivative there, is even less than it was before. Make sense? Now you're ready to tackle your economics, right? Okay, let's look at another application of rates of change, and that's linear motion. And I really find their illustration here to be interesting, the way they do it. What they're trying to suggest to you is the car is only going in one direction. And since they put the direction on the vertical axis and the time on the horizontal axis, because distance depends on time more than time depends on distance. That S is not speed, that is distance. Okay? So, since they did that, they illustrate this with the car going up this way. But in reality, it is going this way. And it starts off going slowly this way because it's not changing much per time, but the change increases pretty rapidly here. But what happens here around 160 or so? About 2 hours into the journey. Looks like they stop for lunch, doesn't it? Because it's about an hour, that's about what it takes for lunch. They don't go anywhere in that hour, okay? So their linear displacement is 0 then. Then they take off and go at probably even greater rate of speed than they did here. Oh, whoops. Wrong road or something. I don't know what it is, or maybe they reached their destination. I think they may, and they turn around and come back, and then they're right back where they were here, because this is a linear distance. This isn't a displacement in 2 dimensions, it's just did. So they went up, stopped, went up again, stopped, just instantaneously stopped, started backing up here, stopped again, and then took off again. Maybe they got down the road here and realized they left their wallet in the restaurant, okay? They went back to the restaurant, found their wallet and stuff, and then took off again. I made up that part of the story. It's not part of the movie, okay? But that's a graph of distance versus time. Remember, you're only going in a linear direction. So it's do it here, slowly a bit, speed up, slow down, stop, take off and go, stop and come back, stay for a little while and take and go off again. That's what's happening here. I guess that's why they drew the car over here. One-dimensional motion, okay? Now they let the distance be S, okay, linear distance is s. That's the position of the car, goodness gracious, relative to the origin, distance from the origin with respect to time. Velocity then would be the rate of change of position with respect to velocity, and that would be ds dt. So if you haven't caught up with that yet, then S is, on the wrong slide. S is your displacement with respect to time, and the velocity is ds dt. Okay? And that also is sometimes called the speed. Does anyone know the difference between speed and velocity? In everyday English usage, we use it interchangeably, meaning the same thing. In physics, and supposedly in math too, what is speed? How does that differ from velocity? There's really two ways. In this problem, it doesn't matter one of these ways too much. Okay? Well, it does a little bit. And that's this. Speed is a scalar quantity only having a magnitude. Velocity is a vector quantity having both a magnitude and direction. Now, in one-dimensional motion, the only two directions you have are forward and backward. Okay? That's the only two you got. In two-dimensional, three-dimensional motion, you got a lot more directions involved. Then you get into vectors. But here, you're only forward and backwards. Okay? Or rest. Okay? But speed is magnitude. Okay? Which means speed is the absolute value of your velocity. Because when you're going ahead, speed and velocity are pretty close to the same thing. When you stop, your speed is zero, your velocity is zero. When you're going ahead, again, speed and velocity are about the same. But when you stop and come back, your velocity is now negative, but the speed is basically the same speed as you were here, because it's the magnitude or absolute value of that velocity. Okay? Now, Figure 6, the one we talked about here, shows the position of a car as a function of time. Remember, the height of the graph represents the car's distance from the point of origin. Not the origin of this graph, but the point of origin. Okay. The point of origin here. The distance from here, because it's only going one dimension. It's not that the car is here and one's up there. No. This is time here. Displacement is only in that dimension. Okay? A little bit stranger. Okay? The tangent line gets steeper on the interval from 0 to 1. Okay, here's a tangent line at t is equal to 0. Pretty close to 0. It's hard to say where it's actually starting from. But shortly after 0, the tangent line is gradually increasing until about here it seems like it's constant here for a while. Almost a linear, a straight line here. Okay, and then somewhere up here the rate of change of distance per time starts decreasing. Okay, as he's coming to this place, the diner where he's going to stop and eat lunch. Okay, so he slows down and finally stops and is there for an hour. So the rate of change here is 0. And then he takes off and goes at, I said, a much faster rate. It looks like here. He ate there too long until he realized that he left his wallet, had to stop. Instantaneously stop, turn around, come back. So his velocity is now, linear velocity is now decreasing. He's coming back toward the origin here. Okay? And then stops again, takes him about 15 minutes to find his wallet, and then turns off and makes another wallet part. And takes off and continues upward again. So, speeding up or slowing down, the tangent lines get steeper on the interval 0 to 1. That's what I was just showing there. So it's increasing in speed. Okay. They get flatter on the interval 1 to 2. Okay. Because the slope of the tangent line is decreasing here. It's absolutely 0 at 3, standing still from 2 to 3, returning to the same spot it rises and falls from 3 to 4. You're back where you were at 3 when you're at 4, and then you take off and go again. Beyond. Now, how would you talk about average velocity on that graph? Instantaneous velocity is the slope of the tangent line. What would the average velocity be? Displacement over time over an interval. If you're 0 to 2, you are here at 0, you're there at 2, do a slope of that secant line there, that gives you your average rate of speed in that time interval. Okay? Average rate of speed between 2 and 3 is 0. Average rate of time, average speed between 0 and 3 would be here. You're not going any further than you did at 2 hours, but you've taken another hour. So the slope of that secant line is even less. You could do 1 to 2, 1 to 3. Yeah. You could do any average that you could anywhere. If you did the average from here to here, that's positive. From here to here would be negative. Okay? Not the same as instantaneous, but in the same direction as instantaneous. Okay. Now, this, I think, refers to example 5. Let me read it and make sure that it is. A truck enters the off-ramp of a highway at t is equal to 0. Just start your stopwatch there. He enters the off-ramp of that interstate. Okay? Its position t seconds later is s of t is equal to 25. Whoa. Okay, no. Sorry. I'm going to have to write here. S of t, displacement as a function of time, is 25t. Yeah. Is it? Oh my goodness. How could, woo, it's past time. Why didn't you stop me sooner? Okay, we'll pick up with that one on next time. Okay, example 5. Sorry, I'm missing part of my lunch now. You let me go too long. Okay. Homework exercises here. I think you can do any of the odds 1 through 7. And you can start trying either 9 or 11, because we've sort of hit on that, but we haven't done. I'd say just do 1 through 7. You got most of the others to do, so 1 through 7 will do fine. We'll pick up the rest of them next time. Good deal. Any questions? All right. Sorry about that.